So today we are actually starting a new lecture. I did upload new files. It's called Lecture 5, something in your online system, Canvas. So if you go under Files and Lectures, you will find the file. And we're actually going to start discussing root finding. This is actually the first topic that is actually sort of a numerical analysis topic. So far, we really just had the introduction. We introduced some basic linear algebra concepts that we cannot live without. And then we went through basics of programming, and we introduced the programming in the context of MATLAB programming environment. So most of the concepts are similar to any other programming environment. MATLAB is relatively simple to use, which is why we're using it. Everything else has a little more friction to it in terms of getting started. So in that sense, MATLAB is widely accepted in engineering programs as a very good teaching tool. So basically all of the details we kind of worked out through MATLAB. So now we should be in a good position to actually start effectively using it to solve actual problems. So one of the first topics is going to be root finding, which we'll start today and we will spend a number of lectures on. And our main topic will be actually systems of linear equations, and we will probably just touch nonlinear equations because they're a little more complex. But one of the one of the major lectures of this course is system of linear equations that show up everywhere and anywhere. And then we will move on to curve fitting. We might only again just touch interpolation, and then we will move on to what I will call numerical calculus, some elements of integration and differentiation, as well as ordinary differential equations in elements of solving ordinary differential equations. So this is our plan. So now we're actually starting with the bulk of the course, which is solving different types of problems. So here's one example of root finding. I guess you could, if you want to show your nerdy self on 6th Street, you might actually, or on a party, you might actually try to use this. Use with caution, okay? Might not work for all majors, how's that? But if you're hitting on another engineer, it actually might work. So the basic problem is, I have a given volume, okay? And I'm wondering how deep should I fill my glass to actually have that much volume of wine in my glass. And this works, of course, also if wine is your preferred drink. So basic problem is like, okay, I know the volume, now I need a formula for that volume. Okay? And basically once I figure out the formula, so I'm thinking this red wine glass, it's actually a spherical cap. For spherical cap, I have analytical formulas. So basically I can work out, we're not going to go into details, but you can actually work out, given the height, you can work out what this volume is in terms of height, as well as this radius in segment A. And once you actually do that, you get the volume as a function of height and radius of the cap. Okay? So this is the information you know. What you don't know here, so you have a desired volume. What you don't know here is this h, and you're looking for h. And this is actually a cubic, so this is not a quadratic, but a cubic formula. And even though cubic is relatively simple, there are some solutions to it that you can actually work out an analytical solution. Actually, you have sort of like a nonlinear equation, and the way we pose these problems mathematically is we pose them as some function of h that I'm looking for is equal to 0. So in this case, all I need to do is take this volume formula, okay? And I put this actual volume here on the left-hand side, and it's then equal to 0. So mathematically, we pose these problems as f of h or f of x or f of whatever else that you're looking for is equal to 0. That gives us a common framework for solving all kinds of problems. So the formulation of the model or of the problem is up to an engineer, okay? And we will now or in this lecture in general, discuss methods that help us solve any problem that is formulated as f of h is equal to 0, and h that solves this equation we're calling the root. So basically here I might have this equation that I want to solve for. There's another equation that can pose such problems that we commonly use in petroleum engineering or in chemical engineering, and that is Peng-Robinson equation of state. So I know for an ideal gas law, PV is equal to RT. Okay? So basically, given any pressure, either pressure and temperature, I can find the volume. Given volume and pressure, I can find the temperature. I can do permutations however I like. Everything is very easy to express in terms of the other. So as long as I know 2 out of the pressure, volume, and temperature, I know the third one. Okay? So that's a simple, very simple equation, except that most of the gases and fluids in general that we deal with in petroleum engineering are very far from ideal. And even if they're maybe ideal, they're certainly not in ideal conditions. So the moment you're at the high pressure and temperature, even if you were ideal at the room temperature, you're not going to be ideal at that high temperature, or you're not going to behave that way. So basically we cannot always use ideal gas law, even though if we have nothing else, that's what we resort to. Okay? So Peng-Robinson equation of state is more of a, it's not an exact equation. It actually comes from correlations. Okay, so it's fitted, and it's fitted in the sense that pressure is this very nonlinear equation of temperature and volume. Okay, and I have parameters here A and B, which are different for every different gas, and for methane they're actually given here on the side. Okay, so if I have pressure given as 50 bar and temperature is 473 Kelvin, then my volume solves the following equation. My F of volume, this is 50, which is my pressure, minus this term is equal to 0. Again, I'm presenting it in this form, F of volume is equal to 0, to be in a general form that we can actually then solve all of the problems with. Okay? So this is another example, and this is how I would find what is my actual volume given the pressure and temperature, for instance, at depth in my reservoir. So if I'm wondering what methane does at 3 kilometers depth and temperature that is at those conditions, so I know basically the pressure and temperature that are common for those conditions. I will plug it in and I will find the volume of methane that is at the bottom of the well as opposed to the top. Okay. So this is a very common problem that we might encounter. Again, this is a very ugly, pretty and ugly is relative, but it's not easy to solve. Okay, I'm not going to call it ugly, but it's not easy to solve, so I need some sort of a numerical method. I don't have a formula that gives me what is VI directly. Okay, so I need to look for it in some way. Here's one more problem, and this is just to give you multiple examples. It's falling parachutist. We know that when you're falling down, gravity pulls you, and there is basically gravity pulling you down, and there is a drag force that is acting in the opposite direction. That drag force depends typically on your shape, okay, and your velocity, as well as actual gravity itself. So basically, there's this. You could express the drag force as C, which is a coefficient, and V, which is velocity. Okay. And this coefficient is typically known for known shapes. But if you're presented with a new shape, let's say that you're in aerospace engineering, okay, or in automobile industry, you're looking for the new shape of a car, you're going to do experiments or simulation with that particular shape that will give you what C is, and then you can predict in a new situation what your drag force will be. Okay? And that's of course important in accelerating and whatnot. Okay? So you might want to do some experiments to find C. Now basically I need a formula, so I know what are the measurements that are going to actually help me find C? Well, my mg, which is the gravity, minus cv is equal to m times acceleration that I can actually measure. Okay, so this is the total of the forces. So when I plug it into Newton's law, I can actually express, after integration, velocity in terms of c. Okay? And velocity is something that I can measure. Okay? So once I plug in things that I know in this relationship, I can again formulate this as some function of c is equal to 0. Okay? So this equation is basically just translated to f of c is equal to 0, and then I can solve for c. Okay? So once I solve for c, then I can use it in any predictions later. Okay? So these are some common problems. Again, pretty or ugly is relative, but this is not something that I can easily solve and just give you a formula for C. So I need to resort to some other methods, and those are the methods that we are going to learn about in this lecture. Now here's one situation where we actually have a formula, okay? And this is quadratic equation. So quadratic equation, I'm again in this form, f of x is equal to 0. And I know, in this case, what x1 and x2 will be. They're going to be given by plus and minus version of this formula. So again, many problems don't have analytical solutions, and for those problems that don't, we have gone through 3 examples. We need to actually develop numerical methods and approaches to actually solve, meaning find an approximate solution. Solution is never going to be exact, but it's going to be very close, hopefully, to the actual solution. Okay. So here's just an overview of our plan. Okay. On the right-hand side, there's these 3 examples of equations where I might need help of numerical methods to actually find the roots. Okay. We will go through so-called bracketing methods. We will first start with the graphical method in a moment, and then bisection and false position. And if you're interested in reading, that's chapter 5 in Trapper's textbook. And then we will look through so-called open methods, fixed point iteration, Newton-Raphson, and secant method, and that's the chapter 6 in the textbook. And then there's also solving for polynomials. We will not go into details. There is a whole theory behind this, but this is just some of the methods that you might have already mentioned in your calculus class. So we will mostly focus on these bracketing methods and open methods because ultimately they can be applied to any polynomial as well. Now, what is the basic difference? Basic difference between these 2 methods is that bracketing methods, as long as I know a bracket, meaning, let's say that this is the root I'm looking for, bracket is an interval around it. If I know that interval around it, I'm basically guaranteed to find the root. Maybe slower, maybe faster, but I'm guaranteed to find it because I know where to look for it. Open methods, they start from one point and try to search for the root. And sometimes, well, you can see here, I don't know how this function continues, but let's say that it just continues. Let's say that you for some reason start searching at 8, and you actually start searching on a search that takes you to lesser and lesser roots. You will never find the root you're looking for. So in open methods, there is a chance that you're not gonna, what's called converge. You're not gonna get to the solution. But if you actually start converging, then those are much faster methods. So there is never, we will learn that there is never a free lunch in numerical methods. Okay? So basically that's the fundamental difference between bracketing methods and open methods. Bracketing methods, after I have a bracket, I'm guaranteed to converge, but I might be slow. In open methods, I'm not guaranteed to converge, but if I am converging, I'm going to converge quickly. Okay, so let's do an example. Open up MATLAB and take this as a function of C. This is our flying parachutist. Okay. So give yourself a range of C's and plot this function for those C's. So my idea is like, okay, I don't know anything about this function. Let me plot it. And then maybe I'll figure out what could be a way to search for it. So program. So basically this picture already suggests some C's. I'm going to go from 0 to 20. So how I'm going to give myself a range of points plot?
0, 20.
That's just everyone. Well, that works. Let's go with that.
How would you use? How would you get an input of ranges? Like, could you say input something colon input?
Oh, so you want
To be
user? Yeah, you would use input.
Can you just show how that works with this?
So let's actually say C1 or C lower. Something like this. And then you type it in, 0. And then you're going to say C higher as input, give me higher C. I'm going to leave space now. And it's going to ask you, and you just put 20. So that's your CL and CH. Now they're read in. You can see them right here. Okay. And then your range C is CL to CH. Yes? Or you can use linspace. This just gives every one I have a value. Okay. Now I'm going to compute F for that. F is 66738. I'm going to get a number of values for all of C's in one formula using vectorization. Should I just divide by C? I'm mimicking this formula. I need to serve coffee today. Is this correct? What I wrote? No? What do I need? Period.
If you stored C as an array, would that still work? I mean, would you still need the period?
Yes, I have to use a period. Or else I will not get point-by-point value for every C.
Being an array doesn't force it to use point-by-point value.
Right? If you don't know what's happening, try. Okay, so times .146843 C minus 40. So now I can see double values for F. If I'm wondering how they look like, here they are. I had trouble calculating, well, the one for 0, it had trouble calculating. So let me stay away from 0. So CL, I'm just gonna lower value, I'm just gonna add 0.1 or 0.5. just gonna use linspace. Dividing by 0 is an issue. And sure, let's work with 20 points until I need more. Okay. So now if I plot that, I can just use plot function CF. And of course, I am very much as usual. I never actually got to figure out how to set it. I didn't spend too much time on this, but how to set the axis to always be large font size. And I can actually see here where 0 is that I do have intersection with the graph of the function. Okay. So I have some function. If I replot with blue and also add circles to it, I can also plot C and zeros of the same size in black. Oops. Okay. So I can actually see that there is an intersection around here, which is in between 14 and 15. Did everybody get this? If you did, let's zoom in. Now, how would I get closer to this root? So somebody gives me 14 and 15 or 14 and 16. And I can see something at 14, okay? The value here, or I'm a little off, I'm at 0.5, I think. This value is positive, okay? And then this value is negative. And I have a continuous function in between. If I find two values where this function is positive and this function is negative at the other end, and I have a continuous function, I have to hit a 0 somewhere in between, positive and negative value, right? And I'm looking for this point where the value of the function is 0, so it intersects this 0 line. Yeah? So now I'm trying to look for that. How am I going to zoom in? So I'm given these 2 points, okay? How could I devise an algorithm that would kind of consistently get closer to my value of the root? Any ideas? So I can look at the one point in between, right? And then what?
Compare that to the next value.
So how do I compare? I look at this segment and I look at this segment. Which one do I pick? How do I pick the next segment that is half smaller? If statement, yeah, but what am I going to check? Closer to 0, or what is the rule? The rule here is actually that I have to have a positive value and a negative value, and then I'm going to have a 0 in between those two values. Okay? So if I take this half here, okay, I'm going to have a positive value, negative value. Yes? So which of the segments should I pick? there's this segment, this half, where I have both positive values, or this segment where I have a positive and a negative value. The other one, right? Okay? Okay, so then I can actually do the same again. I'm going to half the segment, okay, this now, and this is somewhere, half is somewhere here, and I'm going to check again, okay, which of these two new limits actually have a positive and a negative pair. And then I'm going to keep zooming in. Does that make sense? When am I going to stop? How do I set that?
And you're going to do it until you have a desired tolerance.
Yeah, so my length of my segment is how close I am to my root. I can decide what is close enough. And we discussed that before. If I'm trying to measure distance between here and San Antonio, I don't care about millimeters, right? So I don't have to be compared to my mile or kilometer distance to there. Millimeter means nothing. So 10 to the minus 6 is very small and very close, right? Relatively speaking. So 10 to the minus 6 of that kilometer distance, right? So I can set where I want to be based on what my problem is. Right? So basically I'm just going to keep iterating and checking. So we actually came up with an algorithm here. So essentially, this is the way I'm going to say. So there's actually a theorem in math that tells you if you have a continuous function and there is an interval with the lower and upper bracket such that my function has opposite signs of that interval, okay? Either first one is positive, the other one is negative, or first one is negative, the other one is positive. Then basically there's at least one value or one place where this f hits a 0 in that interval, okay? Now, if you actually want to find what am I going to check with my if statement, okay? Then if the signs are opposite, then f of that lower bracket times f of the upper bracket is less than 0 because they have opposite sign. If they're both positive, this will be larger than 0. If they're both negative, it's going to be larger than 0. Okay? So what I'm going to check in this iteration is f of xl times f of xu is less than 0. Okay? All right, so this is essentially the idea. This is my bracket. I found a positive and a negative value, and then I'm going to keep halving this interval. So this is my half. Out of this interval and this interval, I'm going to pick an interval where, again, I have positive and a negative value for f at those ends of the interval. So that's going to be this one and this one, because this value times this one value is less than 0. And I'm going to keep going, okay, until I'm happy. So this is a graphical way to do it. Okay? So for instance, in this particular case, I need to bisect in half. If I, let's say, go between 12 and 16, in half my value will be 14. Okay? And then I'm going to check, is f of 12 times f of 14 less than 0, or is f of 14 times f of 16 less than 0? And based on that, I'm going to adjust my brackets and keep going. Okay. So this is actually an algorithm that I'm going to ask you to program right now. So open up and give me a script and we're just going to, in this exercise, use function that is slightly prettier than parachute is. Or I would think so. It's just simpler looking. So you're going to create the function, and in this process, in this algorithm, I need to evaluate functions. So create yourself a function that evaluates this and call it f. And then create a script bisection.m that actually basically implements this bisection method. But you will have to have that starting lower and upper limit to go with. And we will, all three of us will walk around and help out. And please work on this now because I will ask you to submit this by tonight online.
So this method work if there were multiple routes?
It will find one of them. It will zoom in on one of them, but not the other. And that's a standard problem with root finding. Any numerical method will find one of the roots. And in bracketed methods, you're guaranteed you're going to find one of them. But if there's multiple, then you need to know what is the next next bracket to look. Once you find one, you kind of move away from that and try to look for the others. And when you have functions that are given by formula, you can plot them. In data, you can do the same, but you could have noisy data, so that can be more problematic for actually some functions that are actually just plots of some values like you have in bell logs and whatnot. Well, zooming in just a picture. But what you want to plot also, you want to plot that zeros of the same size as x, so then you see an intersection. So you just plot x and zeros of size of x. Does that make sense? So for every x point that you have, you plot a zero.
So X.
It's a graph of zeros. That line on the interval that you have. So does that make sense? So plot x, or first say it's hold on. Same graph. And now say plot x over zeros of size of x. Size. So basically, yeah, plot, you always plot points. So to plot the zero line, you have to have, for every x value, you have to have a zero. So that's what we created the zero. So you just find yourself.
That's very small. So it's only two or just a small?
Hard to find.
So I'll make F of L.
So basically XL. Yeah, so that's your good starting point. Now you can-
Yeah.
Are we using like the six in this?
Midpoints, yes.
Okay.
So that's your divide x in half. The midpoint, XR is a midpoint, right? XL plus XU divided by 2. Did you find a good? First step is plot that function and find good XL and XU.
Oh, I was just having the inputs and then using them as wide as I
Oh.
want and then let it run.
Okay.
So X of L is
That work? So did you compute it?
Oh, not yet.
Give yourself, try it out. Even I would try it out.
What die should we use?
Hmm?
Yes.
Well, just try something. So that's part of the, like, I don't know. I know because I tried, right?
Yeah.
But in any other problem, you gotta try, plot it, see where you go. I mean, this is a cubic function that is up to 3. Polynomial of order 3 has 3 roots. It's just that some of them might be complex. If it's less than 0, that's not this. So then the other. So out of the 2 possibilities for next interval, the other one should work. Does that make sense? So you have 4 and 5, and then you're saying that it will.
X of L, which is
What is your? How did you create that? Well, F is evaluated in 4 to 5. What you created is an array called F. So F of 4 is just the 4th element of that array. So whatever X it corresponds to. And F is 5 is just the 5th element of the array. So you need a function that calculates F of X to X. So you created that was great for actually investigating, plotting. So now you need a function that will always return F of X to wherever you need it. Yeah. And those are probably a function that's So when you give it an X, it's gonna compute actual F of 4. Whereas right now it's just F of 4 is just your 4th element in the array you created. Could have been 1, 2, 3, 4, 5. 4th element would be 4. This is
Misses the
Yeah. Hello?
I'm gonna do something.
Let me show you. So you have F here. What you're plotting by F of 4 is this.
And I want actually.
Right.
4.
So F 4. F 5. So that 92 is multiplied. But this is not function that you evaluated. It's evaluated which is 3.1. Which is 4.2. Does that make sense? So you evaluated your F's for these values
I'm
of
assuming
X.
the 4th point. I want actually
Right.
the 4th.
And you actually want F evaluated for 4.
Okay.
Number 4. Not 4th in a row.
That makes sense.
Yes.
Yeah.
So again, computer always does totals.
Mm-hmm.
So did everything right. But we're looking at. So if you have this F of X, X cubed, so it's a polynomial, right? And that's polynomial systems. That's where X is where F of X is. At least since there's 3 of them, it's not right. There's at least one real. So we know that we're searching for something that exists, which is why this is. Right. So do you understand the algorithm, how I would get there at some point?
So like you're trying to get to X and then you add them and then one of them.
So if I have a function, so I plot this function, that's a plot function. So let's give it X. And I'm just gonna now try X is 0, presence of values of x. I'm gonna say f(x) is x cubed minus 5 times x squared plus x plus 15. So that should give me f of x evaluated at these values. So basically then I will have to find somewhere, so there is one root around here, and there is one root around there, we can pick one, oops, not pick one here. So this is how you actually plot that intersection. So, oops. That just the zeros for this side. So then it's easy. So I have one root with usually, and one root with here. Because I know that it has to cross zero somewhere. So this algorithm here is just trying to so now this plot gives you where to start. So you can either choose sort of this which kind of limit, which specific limit zero, it doesn't matter as long as f of the lower limit has f of example zero. That means this one is positive, one is negative, zero crosses.
Maybe that was no.
So that's gonna be the test. So basically, let's say that is here. So you're gonna replace with you're gonna replace the lower value with this mid or upper value with this mid, depending on whether f of x r times f of x u is like a or the other. So we're gonna try to look for the next segment for the same value. Make sense? Anybody else? Hold on. Alright. I mean, is bored. You have something to do. He needs you to ask questions. Sitting right there.
So
So you can look at my
Okay.
how do you get this in the box?
Values I hope so. What is 5 cubed minus 5 cubed? It's 0. Yes, 5 plus 2 plus 5 plus 5. Correct.
It's a little sketchy with the same
And then I'm trying to store a function as an array.
What's-
I can be like return like.
Oh.
F4 is equals to
Because we
Okay, so why
don't
am I
have
writing
x.
it?
So your last x, your x is always remove x. Don't do anything with x. X is coming with an input. That's it. So suppress that.
Oh, because when I
So then you won't get to it. Say it.
Understanding, I don't call them things.
Alright, so what you were doing, you came in with x, and then you said x is equal to 5.
that makes sense.
You want always the same answer.
Thank you.
Again, computer does precisely what you tell it.
Start reminding me of this.
If you want to pass inside the function,
Yeah.
So I guess skipping that and just looking at trying to make sense of those two.
You can just, you know, whatever you need to map from the users, you can just put it as input function. If you want a lower value, lower value, see higher value, both of them can
list of values, and then we move on step 2. You also have
No, MATLAB doesn't understand vectors. Then you say if you want to function, and later you said like MATLAB doesn't understand that as a function. There are some ways to define it as a function. One of them is there's a function defined as plus, like axon. You can just put it or you need to put that function outside. As I understand, it says let's do the function and have another function outside of this. Yeah, you need to have another function on that. Then you can just only use your x.
Okay, so I should like type it in command first, and then
Or in the comments, no. You need to write in the function. I would say that. Just this part should be inside. So when you send something, you put it on the other side. And you get it out. This part should be inside. Okay.
thank you.
That was correct. Sure. That's very, you won't get rid of one of mine. Let the computer go. It's a function.
yes.
So if this is then by x, I would say x8. So I had lower, upper, and you want your next segment to be XR is your shape. So the lower point is XR, the upper point is if that's the correct. So here, this is the situation. And on your next step, this is the one you want, right? So you want this to become the lower.
No, wait, no, that's totally not fixed.
So
As long
Excel,
as you have an equal sentence.
otherwise, your Excel remains the same, but your upper is no longer. Right. Yeah. So then otherwise the other
Now,
thing is correct, so you're,
the max that doesn't understand.
so you're moving,
then
in
you
this
mean
case,
the
you want to
function.
move your lower limit.
It doesn't matter, that's the question. You need to have another
Say
function
it's the same,
outside of this.
and it might actually, its value might be changed, so here you
F.
say
And then
else.
it's calling that number and inputting lower number into it.
You need
Does
to
it make sense?
put the lower and upper here, but then you also
It's gonna
check
terminate
that
when it
F
gets
of
close to
X.
X, it's gonna be fine.
F
But
of
you
X
do need
has
to
for
actually
you
put
put
this else
this
below.
then you need to
Say
call
else
We're gonna talk about it.
X use it, because otherwise it's this other, right? And then it's gonna terminate, otherwise it's not. Does that make sense? Just the function,
Yeah.
the first part, yeah, but you programmed it already, it's something that returns the value from the next, that's all. Doesn't, what you have to on your own, you have to plot, find what Excel and Excel.